next. So I guess I should move along to that. Apologies.
Yeah, that'd be great. Yeah, save the asterisk or the Christmas stars for later. Does anybody have a Christmas star besides Bob and Ed? All right. Well, if you're not interested in mEforth graphics and sound on the web, now might be the time to write your write your Christmas star or not. I don't propose to move away from Brad's talk and do that right now. All right. So on with the show, Brad.
All right. So this is a bit of a reprise of my prior talk from Fourth Day. I had a little bit of demo fail. I'm fingers crossed. Hopefully the demos will work today, and that's actually the main reason I'm going to represent this one, because I had a set of demos lined up and then changed one little thing as one foolishly does right before a presentation, and then had a bunch of things break on me. So I'll very quickly blaze through this, but basically to recap, you know, I've been working on a variation of eForth, micro eForth, for a while. It's known as ESP32 Forth in the ESP32 community because that's a catchier name. And it supports multiple different platforms. It does run on Windows and runs on Linux, as well as the Windows subsystem for Linux. You can run it in Linux on a Windows machine if you're set up to do that. And then it runs in a bunch of different ESP32 variants. And relatively recently, I finally got the web version working. In fact, I had intended to do the web version from the early days with it, but hit a bunch of issues and then didn't get back to it until relatively recently. Why the web? Well, as you just saw with the haikus, because it's easy to demo. It's portable. You can point folks at it. They can try a thing out. You don't have to convince them to run something that they might be scared to run some random exe on their computer. So they can distrust you and still run it. And it can be fast. We can do, as we just saw, fast animations, and the web is quite powerful these days. And actually, in some ways, the web is an easier platform to target than some of the platforms out there, because it is an API surface that has a fairly rich community of multiple different implementers, and so they push back against complexity. If you've got lots of different implementers, they all don't want to have to clone everybody else's bugs, and so they try very hard to have a standard that is clear enough and easy enough to implement that multiple different browser vendors can do it. So the micro eForth approach it basically is that most opcodes are defined in a fairly small number of lines of C code, 1 or 2 lines, and then there's a few system variables that are in a C structure that are used to sort of glue things together, things like the tib or the base, things of that sort. And then there's really 5 core opcodes that are sort of the pieces that are of the system that are too complex to do in 1 or 2 lines of C code, but are sufficiently foundational that you need them before you can do the rest of the system in high-level Forth. And so my goal is to have the C that I am producing be minimal in a few lines for each opcode, and then keep it to a minimum in terms of the complex words. And a critical thing there is to avoid needing to build loops. At the point you need loops, that's when you need the interpreter there. That's when you need sort of more of the system up and running. And so I've found that there are about 5 core opcodes you need for that, and then everything else is high-level Forth and boots up from there. So the core of the system really is just this. It's quit, where it's doing evaluation of a single word over and over again, and this is actually the only loop that the sort of basic system has to sort of manually go through and compile before the real Forth interpreter is up and running in higher level Forth. And so then the challenge is, how do you implement eval1? Well, these are the five magic words. It's the ability to parse a number and convert it into, which depends on the base. The ability to just parse and chop up a word, and that depends on the input buffer. The ability to create a word, the ability to find a word, and then the ability to evaluate. And evaluate makes some use of the interior of the others, but it does it not via their Forth definition, but rather by sort of reaching in and calling that code directly. And these are sort of the ones that are need to be exposed out to Forth later. And the things on the right are sort of the core system variables that you need to have. And notice I've got this not found word, which is a variable that holds an execution token to be executed later in the event of an error. And this solves the problem of not needing to have implementations of throw and catch, for example, available and ready at the point that you're doing evaluate. So you sort of defer the problem and say, well, I will eventually have this word that I'm going to execute. Now, if you actually have an error early on in the system, typically I'll initialize that to just be drop or something to that effect. And so then you can have some very confusing errors before the whole system is up, but that's sort of all you need to get there. It's an indirect threaded Forth. It uses single cell opcodes and for the VM. So on the native platforms, you've got in the code position in the word, it's the address of a label in C, and I use a feature called computed gotos, which is not a piece of standard C, but is supported by both Clang and GCC, and the Arduino tools, which are derived from GCC. And then on the web, I'm using really an opcode in that position, because there's only a limited sort of baked in. So it's really indirect, but then there's an opcode in the code word position. And the main reason I keep that indirect threaded structure is it makes both C and does a little bit simpler. It might be worth considering other models for performance, especially in the web. There's a little bit of performance lost to sort of that indirection. I have unlimited size stacks, so unlike some of the other eForth variants where they will have a sort of I guess you might call it it's not exactly a Harvard architecture, but well, separate stacks, separate stacks that are not in the memory space. I have stacks that are in the main memory space. I support 32-bit floating point primarily because ESP32 has 32-bit floating point in hardware, and I wanted to expose that, but I don't do doubles, and I avoid counted strings and instead do address and count everywhere. So how to bring this to the web? Well, I wanted to convert to a thing called ASM.js, which I'll explain in a second. It's just a way of a particular style of JavaScript that has some performance advantages. And so what I did is I hand converted those 5 core words because they involve loops and are tricky. And then I wanted to automate converting the rest of the opcodes using regular expressions. And much as I was expressing some regret about the way that the Forth Haiku works with sort of doing simple string substitution, this also probably was a mistake. Anytime you're solving your problem by sort of trying to do string matching and substitution, if it's anything other than the most trivial cases, it adds a lot of complexity. And so in 2020 hindsight, I probably would have been better just to have 2 different versions of the opcodes, one in C and one in JavaScript. The conversion was almost, it was more trouble than it was worth. But anyways, the particular type of JavaScript that I target is a type called ASM.js. And this is, I think, the best hack I have ever seen. It is an attempt to embed C code in JavaScript. And why would you do that? Well, as one of the former CEOs of Mozilla once said, if you want your JavaScript code to run fast on the web, what you need to do is pretend that you're writing C code and write it that way. Well, it turns out that a lot of the JavaScript engines are struggling against. JavaScript's an interesting language. It has a lot of sort of heritage that's inherited from Lisp and lexical scope and things like that. But fundamentally, a challenge that a just-in-time compiler, as all the major browsers use for JavaScript on the web, have is that if you're going to make your JavaScript engine fast, you have to recognize the data types of all of the variables. And JavaScript instead has duck typing. It has a variable can contain a string, it can contain a floating point value, it can contain a number, and so where the JavaScript interpreter can figure out that a particular variable is always of a certain type, then it's able to generate machine code for it. And so ASM.js is an attempt to do that in a systematic way, and it's converted on the Chrome implementation, because I happen to have been the guy that had the job of implementing it. I actually implemented the code that Chrome uses to take the ASM.js syntax and convert it to this other representation called WebAssembly, which is an even newer representation that browsers are able to more directly translate into low-level codes. WebAssembly is actually a set of opcodes that can actually be sort of directly compiled by now actually all the major browsers. But ASM.js is easy to generate, which is why I used it for this particular project. It's text. WebAssembly is a binary format, and that's a bit of a pain to generate. So the way ASM.js works is that you do extra work to make the computer be able to do less work. So, for example, if you want to offer a hint that a particular variable is an integer, you do a ridiculous thing. You OR it with 0, which has no effect on it directly. But because the language semantics of JavaScript are that when you OR something with any value, it assumes that you want to do that with integers and not with strings or floating point. It is a hint that this is that this is an integer. And similarly, there's this function fround that rounds something to the precision of a 32-bit floating point value down from a double, and that is a hint again that that this might be a float 32. And so the way this works is that if you're, for example, doing an add, you're adding 1 to a variable. If you don't OR with 0, well, that might overflow beyond the range of an integer. But since JavaScript would normally treat it like a double, now it may think you have a double. So by ORing with 0, you're indicating to the JavaScript engine that no, this is really a 32-bit integer, and you can actually generate machine code that will give you a 32-bit integer. And the same thing with multiplies, and there's a bunch of things. And then when you access memory, the way that it works is that you are to create a single array buffer. There's a data type in JavaScript called an array buffer that allows you to have a typed array where you can get multiple different windows into that array, where it becomes an array of just int 32s or unsigned int 8s or float 32s. And so all of the accesses to memory need to go into that array. And if you do all of that, and you do it consistently, and you put a label at the very top, magic string, actually, just ASM.js is the string, the JavaScript engine will go through, validate that you have followed all of the rules, don't have anything that violates these ASM.js rules, and in that case, it will convert it to WebAssembly, and then from WebAssembly, it will convert it to some very efficient machine code. So what this looks like is fairly unreadable, but this is the implementation of parse that I hand converted that does things like accessing this int32 array to go in and grab things like the tib and variables of that sort. You'll notice there's these extra shifts because one of the ways that you hint that you're accessing an aligned value is you have to say, okay, I've got this pointer into a memory location, but I'm right shifting it by 2 to clarify that no, I guarantee this is aligned, so you can generate a load that will assume things are aligned. And so then for all the remaining opcodes, I go and I take my C X macros, which you see another talk of mine to understand how those work, and I do regexes to convert them to ASM.js. And the regexes are horrible. Just imagine hundreds of lines of sort of cases of where you might want to have a substitution. And there's maybe like only, it took nearly 50% as many lines of code to do the substitutions as there were opcodes. So it was a lot of tediousness. It would have been better off to just hand convert the opcodes. And then the next challenge is to provide bindings, because you're running inside the browser, but you want to have access to JavaScript. So to do this, I actually expose really just two words, this call word and this JS eval word. The call word runs a JavaScript function that's embedded in an array in a particular slot position, and then JS eval bang takes a counted string, or sorry, a index. What do you call those strings? I always forget the naming. Anyways, an address and a length, and we'll evaluate that piece of JavaScript and then put the result in a slot. And then there's also a word that just does an evaluation. And the way that this works is there's this single opcode call, which is done sort of in the usual way. And then it expects to call into a function that takes the a JavaScript function that takes the current stack pointer as a parameter, does some things to pull off variables from the stack, and then returns the updated stack pointer. And then I seed this array of JavaScript objects with a JavaScript function that does that set eval operation, the JS eval bang, and then that's in position 0 of this array. And then I implement this call operation. And then from there on, I'm able to build up all the other words using JS eval. And so the rest of it is happening through the Forth interpreter, doing things like executing some JavaScript code embedded in one of these. This R syntax is a multi-line string that I support. And then I've got a syntax, all of this defined in high-level Forth that I'm not going to go into here, that lets you declare a Forth word with some optional parameters, and then it handles the bindings of passing that into JS. And so, for example, the way that works if you have two variables in the Forth stack and you're going to have a single return value, you get in these variables A and B and can just do inline JavaScript. So think of it as an inline JavaScript, the ability to have inline JavaScript. But notice that it's actually bound sort of on the outside and is going through all of these layers. So the call out to JavaScript is relatively sort of complex and expensive. So most of the time you're running in this fast, low-level Forth, and then calling out to JavaScript. And so from this, I've done some bindings. Here's an example of how swap would work. You can have multiple return values. And then I've added bindings for graphics and sound. And you can create enter a graphics mode. You can show some text. Sorry, there's a text area you can show at the top and bottom, and you can choose how big you want your graphics mode to be. So you can pick a width and a height that you want to work with. If you want to work in 320 by 240 graphics mode, you can choose that, and then the system will scale the graphics to the size of your window. You can get the current position of the mouse and the mouse buttons. You can you can set the current color, and then with that color, you can draw boxes and lines, and you can draw text, and you can pick the font that you want to use for that text. You can draw paths and fill them in, and a lot of this is built on top of graphics that browsers have in their APIs. So you can these are just bindings to the ability to draw and fill in an area. And then you also have a transformation stack, a little bit like PostScript, where you can build up a series of transformations, scales, rotations, and then push and pop that transformation stack. And lastly, you have the ability to do sound. And so with that, I'm going to transition over and try the demos that I failed on last time. If you want to use this tool, if you go to eforth.appspot.com and then click on web, you'll get the web version, and right there you'll have a Forth prompt. It is pretty much the same Forth that is available for ESP32 Forth. I'll even demo that locals work. You can, if you do a word test AB, and let's say we wanted to do a do loop, and let's print out A and print out B inside the loop. And then I pass in 1 and 2, it will print out 1 and 2 over and over. in that loop. And so, and you can even do C on the words, and you get to see the structure of the words, and it translates these the locals into, there's a helper word to let it access reaching deeper into the stack, and then there's it's pushing the values explicitly onto the return stack, and here it generated the R drops that you need to pull out. But anyways, on to the demos. So there's vocabularies in this system, and in the web vocabularies where all of these words that I just described live. And this forth also has a task system, and so you can do things in the background. But one of the words that I've added to let you get things into, one of the problems with the web forth is how do you get something in? Well, I've added a word called import that will load something from a local file. And this will, I don't know if folks can see this on the projector, but this is popping up a dialog box to let me pick a file. And unfortunately, I don't know if I shared the whole screen or not. But anyways, I'm going to go ahead and pick one of these samples. And this sample is using some of these graphics words and I think we showed this last time. If I, down here, I've got this text area. And if I go, back out of graphics mode, I can go back into text mode. And let me just list, actually go back up into the Forth dictionary and list. If I do C here, what I'm running is this running word that's doing update over and over. And well, what is update doing? Well, it's doing it's getting the viewport and updating the window, and then it's drawing the turtle and then drawing the mouse. And so if I go back into graphics mode, I've also got a word here forward that is, oops, it's doing the gate and then backward. And then this is doing a bunch of floating point math to in fact, looks like it's using locals, which is why there's those mystery numbers there. That's what you end up with if you do locals. And so, for example, I can tell the turtle to move forward 100, or I can tell it to make a 45-degree right turn and move forward 100. So we saw that demo last time at Forth Day. That one's nothing particularly spectacular. Let me go ahead and hit reload, and I'm going to go do an import of something else. And actually, to give you a sense, and this is a demo that I did way back for Valentine's Day, but I've now translated it to work on the web, and it's got a bunch of different animations going on. You can click the mouse, and it's doing particle systems where the fire is coming out, and quite a lot going on here to make this happen. And then, but you'll see this is all sort of here. There's a bug actually I've got with this one that it's littering a bunch of junk on the stack. So my stack is much like some of the other eForth. This prints values in the stack, and it appears to have overflowed this one. So that was demo number one. The thing I most wanted to show last time that I got working was audio, and so I've got a bunch of Dr. Ting's Bach that I converted to work in this Forth. And actually, the funny thing, and I can actually, well, actually, let me share a slightly different window. So if I go, let me share this window. So, and actually, the biggest challenge actually in getting this to work was I needed to sort of bridge the difference between how he had been doing sound. But there's one other thing I actually had to add for, oh, actually it's not, oh yeah, for this one. He uses pick, and I, believe it or not, mEforth, I managed to get as far as I did without the word pick. I have locals and a bunch of stuff, didn't implement pick, so I had to do an inline implementation of pick. I should probably fold that back into the, I don't have roll either, so. But the way this worked is that I have added this word poly, which takes in, using locals here, you'll notice, a bunch of different note values and a duration, and then it chooses a color, different colors, and then draws boxes with each of these boxes, and then plays a tone, and then it also checks to see if a key has been pressed, and in that case it throws. And then down here there's a definition of the word octave, which defines a translation from the different note values, which Dr. Ting had actually done as a bunch of constants, but I decided to compact his code a wee bit. And then the rest of this is actually basically verbatim the work of Dr. Ting, and he inputted a huge number of these Bach songs. So I'm going to go ahead and exit. Actually, let me show. It's similar. I've got one of his inventions, and I needed to be a little bit more systematic. Well, actually, while I'm in here, I'll show. This is the code for that heart demo, and as you can see, it's a lot of detail in it. But similarly, I was able to take my my Linux version of this program. It also runs in Windows, actually, and I was able to do a fairly light translation. I would like to eventually make it run from the same piece of code on both the web and the desktop version, but right now there's just enough difference in how they work that isn't practical. So let me switch over to the other window again, and so back over here, and I'm going to go ahead and do I'm going to do another web import, and let's load Dr. Ting's Toccata and Fugue, and I believe I need to type all to make this start, and hopefully folks will be able to hear the audio. Well, I will stop that one there. I'm also going to show one of the. So he's got one file that has all the inventions, and I'll load that one up. Let's try invention number 10. And with that, are there any questions?
I don't have any questions, but I'd like to ask Brad if he would care to go to the challenge portion. I don't think anybody but you and Bob are there. Can you hear me okay?
Yes.
Okay. So since my audio is crapping out, just go when you're done with your asterisk or with your star, with your Christmas star, hand it over to Bob. And Bob, if you would just do your Christmas star first, or if you really want to do it at some other point in your presentation, I'd like to do this. When we start Bob, we'll start the clock and give him 15 minutes, and then we'll stop the recorder. I'll rudely interrupt Bob and and we'll stop the recorder at that point, and hopefully that'll be sort of enough for this meeting.
All
But
right.
I anticipate that my net's crapping out here. So